All right, we are on video 7, which is talking about heating curves. So, believe it or not, if you're talking about ice, so even just melting ice or boiling water or taking boiling water and turning it into ice, takes a lot of energy or releases a lot of energy depending on which way you're going. So each step in that process releases a certain amount of energy. So we were talking about the other day heat of vaporization and heat of fusion and your specific heat capacity. Okay, key thing to remember if you remember, so we have your delta H of fusion equation and your delta H of vaporization. Those do not use a change in temperature or do not take place at a change in temperature. So your heat of fusion is the same thing as melting, so going from a solid to a liquid. Where heat of vaporization is the same thing as boiling. So if you're taking something and going from a liquid to a gas. So just a couple things to remember. If you're going solid to liquid, it's using heat of fusion, vaporization, liquid to gas. So just a couple things kind of recap from a while ago. So solids, we need to remember have strong intermolecular forces, attractions. So they are going to be very close together and they're going to have the strongest attraction. They have a definite shape and volume. And the molecules have just a slight vibration and that's it. Okay, liquids, they're the in-betweeners. So they have medium intermolecular forces. They have shape but not volume, so they keep shape. So shape of container but not volume. So they have a constant volume. So hopefully this is a review. And they have a sliding motion. And then we have our gas. They have no intermolecular forces. That's what, remember, we're back to our ideal gases. And they take shape of both the container. So it takes shape and volume of the container. Just a couple things to remember. All right, so here is what we see as called our phase change diagram. So you'll see this as our heating curve. So here's representing our heat energy. Most of the time, we'll also see the unit of time. Okay, and then here is going to be your increase of temperature. So you're going to have your increase of temperature there. So we have all these different pathways that a molecule has to get through. So for example, this one starts off as a solid because it's a low temperature, and it eventually goes to a liquid and to a gas. So if you look going here, so our problem right there is going to be melting. So this is melting. We're going from a solid to a liquid. Here we're going from a liquid to a gas, so that's going to be your vaporization or evaporation, whichever one you want to look at. And then this is going to be the opposite, so this will be condensation. And then this will be going from a liquid to a solid. So if we're going from a liquid to a solid, we're talking about freezing. So just a couple of things to remember. So these pathways are going to represent a change of path or change of temperature. So those purple are going to all be a change in temperature. Our phase changes, so like freezing, melting, condensation, vaporization, those do not require a change in temperature. So those are going to be where we use our heat of fusion equation. So we're going to go through our first example together. So we have 42.3 grams of ice and it's heated from -20 to 150 degrees Celsius. So we know here -20, well, that's going to be ice. Okay, water freezes at, just going to put that in, 0 degrees Celsius. And we know water boils at 100 degrees Celsius. So we're going all the way from ice and then we're going above the boiling point. So we're going to turn it from ice to gas or water vapor. So we're going from solid all the way to gas. So we know that we're going to have to melt, we're first going to go from solid to liquid to gas. These are all your constants. Okay, you will get all of these on the test for whatever problem you have. So I'm going to draw my phase change diagram, or my heating curve. Okay, so I'm going to go here. I'm going to put time over here, and I'm going to put my temperature. So we know negative 20 is our starting point. Okay, we know we need 0 degrees Celsius because that's what water freezes at. Okay, we know that water boils at 100 degrees Celsius, so I need to include that. And we know that we're trying to get it all the way to 150 degrees Celsius. So we're going to include all those points. Okay, well, we're going to start here because that's our starting point. We're starting at negative 20. And I need to get all the way to 150. Well, it's going to keep going up until it gets to 0 degrees Celsius. And then we know at 0 degrees Celsius, it's going to start melting. Okay, then it's going to start increasing again. It's going to get to 100 degrees Celsius, and we know it's going to start boiling. But then it's going to have to start going up again to get to our 150 degrees Celsius, and then we reached our ending point. So here we have our solid. Here we have solid to liquid. Here we have liquid, and then here we have liquid to gas. In this point, we have gas. Again, that's because we're going negative 20 all the way to 150. So we have to go through all 3 phases of it, solid, liquid, and gas. We have to include our phase changes, so solid to liquid, liquid to gas. So now we need to do our calculations because each step of this is going to give off a specific amount of energy or require a specific amount of energy. So we're going to label our different steps. So we have step 1. Step 1, I'm going to just label them 1, 2, 3. So anytime I change pathways, I'm labeling that as a number. So 1, 2, 3, 4, 5. So step 1. Well, we see that we're doing a change in temperature. So we're going up. So we know if we're using change in temperature, the only equation we have that has delta T is Q equals MCAT. So we're trying to find joules, so we're using Q equals MCAT. And we know we're talking about a solid right now. So we're going to plug in, just going to make a note of that so I kind of keep a note of it when I'm using my variables. So Q equals, if we look at the problem, it tells us our mass. The mass is going to stay the same. We're not losing or gaining. Okay, we're still talking about the same amount. So 42.3 grams. All right, our C, well, we're talking about a solid. So we go to our C of our solid, 2.06 joules times grams degrees Celsius. And then our delta T, which remember, delta T is TF minus TI. So we're going to do TF, which is 0 degrees Celsius, minus negative 20 degrees Celsius. That has a decimal at it. So our sig fig will be 20 degrees Celsius. And our answer will have 2 sig figs because we don't count our constant. So never count constant. So we have 3 here, 2 here. Answer will have 2. So our answer would be 1700 joules. So that's step 1. So step 1 is giving us 1700 joules. But we got to keep going. So then we have step 2. All right, so step 2 right here, we see step 2 is right there. So it's going from solid to liquid. So if we look at solid to liquid, we know that's melting. So we are going from solid to liquid. We're not changing temperature, so we're not using MCAT because we don't want to change in temperature. We're going to use our Q equals M times our heat of fusion, because remember, heat of fusion is going from a solid to a liquid. So I'm just going to plug my variables in. Okay, my mass doesn't change. It's 42.3. Okay, then I'm going to go and find my delta H, F. All right, it's right there. 334 joules per mole. Multiply that out. We know my answer should have 3 sig figs because constants don't count towards sig figs. So we calculate that out. You should get 1,400 in joules. All right, so that's how much step 2 is going to be given. All right, step 3 now. All right, so we did 1, we did 2. So step 3. All right, we see that change in temperature. So change in temperature, we're talking about a liquid, just so I remember my constants. Okay, change in temperature automatically, Q equals MCAT. Okay, we don't know our Q. Our mass has yet to change, so 42.3 grams. Okay, our C, this time we're talking about it in liquid form, so we find our C for a liquid. All right, I find right there 4.184, the one we've been using quite a bit. All right, delta T. All right, well, we're going from 100 degrees to 0 degrees. So our change in temperature, remember delta T is TF minus TI. So it's going to be 100 with a decimal minus 0 with a decimal. So our answer is going to just be 100 degrees Celsius. We have 3 sig figs. So if we have 3 sig figs, we're going to get 17,700 joules. So that's our third step. So we have 2 more steps left. So now we have step 4. We have to do it for every step. Okay, step 4, we're going to look. All right, we're going from a liquid to a gas. So we're not changing temperature. It's a constant temperature. So if we remember our constant or our liquid to a gas, we're going to use heat of vaporization, which is Q equals M and then delta HV. Okay, so we're just going to plug in our variables. Q equals, again, same mass, 42.3. Our delta HV, we're going to go up here, find delta HV of water. Okay, 2,260. And then it's joules per gram. Okay, we're going to calculate that out. Our answer should have 3 sig figs, because again, 3 sig figs, because our constant doesn't count. And then we calculate that out, and we get 95,600 joules. So that's what step 4 is. Last is step 5. So let's go up and find step 5. All right, step 5, we see that change in temperature. So change in temperature automatically, we know, is Q equals MCAT. All right, so let's see step 5. We're talking about a gas. So we're going to find our constant this time for a gas of water. So 2.02. So 42.3 grams don't change. 2.02, we just looked for our constant. Delta T is TF minus TI. Subtract those, so let's look at our temperature. So we're at 150 minus 100, and they both have decimals. So it's 150 with a decimal minus 100 with a decimal. So we subtract that and we get 50 with a decimal degrees Celsius. Okay, our answer, those don't, again, constants don't count. So this is 3, this is 2, so our answer will have 2. So 4,300 joules. So if we want to find our total, we add all steps together. So you do step 1 plus step 2 plus etc. And that'll get you your constants or your total amount of joules. So I want you guys to add all 5 of those numbers and get your final answer.